Namaskara. In this session, we continue our discussions on Fibonacci heaps. It's a very sophisticated data structure, and the discussions related to them will span across several sessions. So I will briefly recall in every session a little bit about what we have discussed and then continue with my discussion. Fibonacci heap consists of several heaps. A heap is a tree in which the values are stored in heap order. So the number of trees in a Fibonacci heap is denoted by T, and every node is either marked or unmarked, and the number of marked nodes will be M, and we have defined the potential of a tree to be T plus 2M. This potential is defined for the sake of amortized analysis. This is not a part of the code or a program or implementation. This is purely a conceptual add-on. This is defined for the sake of analysis. And when we work on a decrease key operation, we perform the operation called cut and then decrease the key. Cut operation will remove V from the child list of its parent, move V to the root list and clear the mark of V if V is marked. These are the three operations that we do. So after doing this, we just check whether the parent is marked. If the parent is marked, parent will also be cut. That is the reason why this is a recursive procedure, and then this recursion will go on until you find either a root or an unmarked node. So when an unmarked node is found, it is marked and then we terminate the process. Therefore, the number of nodes that will move to the root list is precisely the number of ancestors of the node that are marked. So the for a node V, if the ancestors are all marked, suppose these are all marked ancestor and this is an unmarked ancestor, suppose there are C of them. So V is moved, all these C will also be moved, and then you do some operations by marking this. Therefore, the total amount of computation done is C plus 2. This is the actual cost. C plus 2 is actual cost. After moving all of them, notice that they are unmarked. Therefore, the number of marked nodes come down from M to M minus C. All these C nodes which have gone to the root, they are unmarked. In fact, if V might also be marked, when it is moved, that will also get unmarked. So even this may lose, but if V is unmarked, the minimum number of nodes that are going to lose the marking is C. So definitely C are going to C nodes are going to lose their marks. So from MM, but finally this node which is unmarked, is going to be newly marked. Therefore, the new number of marked nodes is this. And then you have C plus 1 nodes going to, so T is going to T plus C plus 1. All this V and all the C marked nodes, all of them, they go to the root. Therefore, T is increased to this, M is reduced to this. Okay, this is increasing and then this is decreasing. Therefore, there is a potential difference. So, if you look at the potential before will be T plus 2m. Potential after will be T plus C plus 1 plus 2 times m minus C plus 1. That is equal to T plus 2m minus C plus 3. This is potential after. Therefore, potential difference, which is equal to potential after minus potential before, is going to be minus C plus 3. You subtract and T and 2m gets cancelled and you have only minus C plus 3. This is potential difference. So, amortized cost which is equal to potential difference plus actual cost, and that is equal to minus C plus 3 plus C plus 2. This is the actual cost and that is equal to 5. That shows amortized cost is order 1, is less than or equal to 5. Therefore, amortized cost is, this means in Fibonacci heap a sequence of alpha decrease key operations, alpha times van Newton will have a total cost upper bound by 5 alpha, which is just order alpha. Total cost less than or equal to 5 alpha, which is just order alpha. This is the important point that we have seen so far. And now we are going to look at the operation called delete min operation. Finding the min is easy. H points to the node containing the min. So, H dot data is minimum value. So, if you want only the minimum value, you can easily obtain it. But if you want to delete min, this is where we have to do quite a bit of work. So, what do we do for delete min? H. So, you have the root list, and in the root list, let us say this is the min is pointed by this, and this has got children, several children. It may have trees. So, let us say you have A, B, C are the children, and then you have trees under A, B and C, arbitrary structure. We remove the minimum, right? We remove the minimum, that node, and promote all the children up to the root list. Okay? So, we have this transformed to A, B, C, all other things are as such. All these children will be promoted to the root level. You can make H to point to the next box because that node is gone. Temporarily H may point to, for example, to the previous box. You move H one node before or after, doesn't matter where you move. So you just move one position, let's say to the left like this, and then delete that node and promote all the nodes. And this can be done in order one time. How we can do this? We can delete the node that's in a doubly linked circular list. That's very easy. Pointer jumping is order 1. So you can throw a node out. How do you move all the children? Remember, every node has got a pointer to one of its children. That means the child circular list is referred by a pointer. I have H pointing to a doubly linked circular list, and I have another pointer pointing to the child list. That's also a doubly linked circular list. So if you have P1 to this, and if you have P2 to this doubly linked circular list, you can merge these two in constant time. All you have to do is that make the next, right, this is splicing, right, under the previous to this. You change the 4 pointers in such a way that it's merged and you get one big circular list. Let's say when you keep going to the right, after coming to the right you just get into the other one, keep going to the right, and then get back here and then continue with this right. Therefore, you can have the right chain visiting all the nodes. Similarly, left pointers can be made to visit all the nodes. Change the left sibling pointer and right sibling pointers in these two nodes so that it's called as splicing, and you get one big circular list. And this can be done by adjusting 4 pointers. That is the reason why you can move all the children. You may have 49 children, doesn't matter. In order one time, you can move all of them to the root list like this. This is splicing the children circular list with the circular list referred by H. Okay. So how do we achieve this in order one time? We achieve moving all children to the root list in order one time by splicing or merging the root circular list with children circular list. By splicing these two, you can move all of them independent of the number of children. Whatever is the number of children, it doesn't matter. The node has a pointer to the children list. That list and the root list can be spliced, and one big circular list can be obtained in constant time. It's a matter of adjusting 4 pointers. So when you do that, you are able to do this, and after this, after moving this, a very interesting exercise is done. This is the most complicated step, and this is called consolidate. Consolidate H. So what do we do in this? The objective of consolidation is in the root list, the trees are going to be merged, and finally we are going to have only trees with distinct degrees. Okay? At the end of consolidation, we are going to have the root list, and that will have trees only with distinct degrees. Okay? So that is what is going to be the objective. So how do we achieve that? Right? What do we do when we find trees with the same degree, that is the root having same number of children? All right. So the first basic operation that we are going to do in consolidation is linking of two trees. Okay, link T1, T2. There are two trees, and these two trees, they have the same degree. The roots of these two trees have same degree. Important thing is that you are not going to link two arbitrary trees. You are going to link two trees, okay, roots of T1 and T2 have same degree. Okay. So, for example, how do I link, let us say 7, 12, okay, I will write a bigger font. 18, 20, 25, 30, 19. This is one tree. Its degree is 3. Another tree, 40, 45, 51, 60, 70, 49. Okay, not visible. I will make it. So here you have two trees. They have the same degree. The roots of them have degree 3. In this, we are going to attach the tree with the larger value under the tree with the smaller value, because in the heap order. So what we do is that we are going to attach this to this. So tree linking will make 40 a child of 7. Okay, this is going to make the child of 7. So if T1 dot data is less than T2 dot data, then attach T2, attach it with T1, else attach T1 with T2. So what do you mean by attaching? attaching T1, let us say attaching T2 with T1. What do you mean by that? Attach T2 with T1. What does this mean? Make T2 a child of T1. Increase the degree of T1. Earlier, for example, in this picture, earlier 7 had degree 3. After attaching 40, okay, so how do you make T2 a child of T1? Simple. Parent of T2 is T1, and then increase the degree of T1, and then add T2 in the sibling circular list of children of T1, because this has become child. See, earlier there was a circular list of this, and now you will have a circular list of this. That will also be added, because that also has become a child now. 40 also has become a child of 7. Earlier 7 had only 3 children, 12, 15 and 18. Now 40 is also a child. Therefore, the circular list containing 12, 15 and 18 is expanded to contain 40 as well. That is what you have to do. So, these kind of things, when you do, the tree linking is done. As you can see, tree linking is order 1 operation, because one parent pointer setting, one insertion into the doubly linked circular list, that is all, and updating the degree. All these operations can be done in 6 or 7 steps. So, it is order 1. So, link T1, T2 means the root with bigger value will become a child of the root with smaller value. Now, you have only one tree. This is heap order. Everything is heap ordered, but now these 2 trees are. Notice that the linking is done only when the roots have the same degree. You are not going to link trees with different degrees. And if you are linking 2 trees with the degree D, it is going to create a tree with the degree D plus 1. As you can see here, earlier 7 and 40, they were individually having degree 3. After merging, after linking, only 7 will be there. 40 is deleted, 40 has become a child now, and the 7th degree will be 4. The degree of 7 will be 4. Okay. This is increase the degree of T1 by 1. That is an increment. This tree linking operation we will do to eliminate trees with same degree, because if I find 2 trees with same degree, I will link them and create another tree with degree 1 more than the previous one. So, I am going to scan my root list, and then I will look for the trees with same degree. Whenever I find the tree with the same degree, I am going to link, and thereby I will eliminate the duplication. So, as many duplication as I find, I am going to keep eliminating it. The objective is, at the end I should have trees only with distinct degrees. I must have trees only with distinct degrees. Okay. So, how do we achieve this? How do I know? It is a very long list of trees. The root list is a long list, and it may have trees of different sizes in different places, and you have promoted and you have inserted new node. Every inserted new node is a singleton, its degree is 0. So, there may be lot of nodes in the tree with several trees having same degree placed all over. They are not available in any sorted order or in the, they are all not bunched together. There may be a node with degree 3, next 7, next could be 1, next could be 0 and then 0 and then again 7 and again 3 and again 0. It could be in any order. So, how do I locate the trees with the same degree? When I locate, I can do the linking and eliminate the duplication, but how do I locate? So, here is a very attractive and interesting bookkeeping mechanism. Okay. So, we are going to have an array of pointers. Okay. This array of pointers, okay, this is you can say a D array 0 dot dot some number. We will figure out that number later. Okay, let us say this is a pointer array, all right. This is a maximum, D is the maximum degree that you can encounter. Whatever is the maximum degree, we will identify that number later. Okay. D0 or Di will hold a pointer to a tree whose root has degree I. That is what Di is going to hold, otherwise it is nil. It is a null pointer. So, we have an array, and in this array we will have pointers, and Di will have a pointer to the root with degree I. Okay. So, we will see how this array is used to locate the duplication, and then we can carry out the merger and all. Okay. So, here I am giving you the root list. I am not drawing the full picture, that is going to take a lot of time. So, this node, its degree is 3. Okay. I am not drawing the full tree, its degree is 3. The next one, the degree is 1. The next is degree 0. The next is degree 2. The next is degree 1. The next is degree 0. Next is degree 2. Let us say this is our current root list. Okay. This is the current root list. And let us say this is the minimum. Your name is referring here, it is a doubly linked list. So, I am going to have D 0, D1, D2, D3, let us say I have initially all of them are null. Okay. Now I have a scanner moving through. The scanner will stop from the name and then it will keep moving to the right in the doubly linked circular list. So the scanner, you can name it as a temp or you can name it as scanner, okay. And currently the scanner is at a node, its degree is 2. So I will set D2 equal to scanner, which means D2 will be pointing to this node. D2 will have a pointer to that node. Then scanner moves to the right. Scanner, this is a scanner. The scanner moves to the right. Now it is pointing to a root whose degree is 1. So D1 equal to S will set D1 to point to this node. The scanner moves further to the right. Okay. Now the scanner is pointing to this. Its degree 0, so D0 is set to S, which means D0 will point to that one. The scanner moves to the next one. When the scanner moves to the next, scanner will point to this. So you will now attempt to store S in D0. Because S is pointing to a node whose degree is 0, you would like to store this reference to D0. But D0 is already pointing to its non-null pointer. That means D0 is already pointing to a node. That means there is a tree with degree 0 already. Here is a tree with degree 0. Now you link them. So one of them will be going down to another. So let us say this node is the one with D0 pointing has a higher value and S has a smaller value. Then the following will happen. I will delete that, right, from the list, and it's not a root anymore. So D0 will be again made null, and this will be deleted from the root list, and it will be linked to this. It will be linked to this. S is pointing to a node and this is deleted. Okay, this is deleted. This the tree has gone under the other one and its degree has become 1. Earlier its degree was 0, the two were merged. Now S is pointing to a tree with degree 1. So we would like to copy this in D1. So when I go to D1, I already see that there is a tree with degree 1 being pointed out by them. So I already have a tree with degree 1. S is pointing to link these two, right. So when I link, let us say S is going under this. In that case, I will delete the node pointed by S from the root list because it is going down, and S will point to whatever D1 is pointing to. So all these things will happen. S will point to, this will be deleted, this will be deleted, this will be deleted, S will point to this node, this you will add, whatever is the degree 1, right, this is degree 1, that is added. Because it is already 1 and one more is added, its degree has become 2. S is pointing to degree 2, and this node has no longer degree 1, therefore D1 link will be made null. S is pointing to now a node with a degree 2. Now you attempt to store the reference S in D2. You attempt to store the reference in D2, but D2 is pointing to some tree. That means there is already a tree with degree 2, tree whose root has degree 2. Here is S pointing to a tree whose root has degree 2. I want to have only distinct ones. Link. So when you link it, let us say this goes under the other one. So this pointer will go, this node will go, this will come under this, its degree will become 3, 2 will become 3, 2 will become 3. So S is now pointing to a tree with the degree 3. Earlier it had 0, it became 1, it became 2, it became 3, right. Now you look into D3, that is null. Now the reference to S will be stored, that means D3 will point to this, D3 will point to this. Okay, D3 will point to this. Now S will continue, the scanner will continue. Once you store S in some D value, S will continue. These information are irrelevant. I have just shown linking. So S will continue. When S continues, its degree is 3, D3 is pointing to this node, S will continue, so S will go to this one. It is pointing to a node whose degree is 2, so D2 will be set here, D2 will be set here, S will go to the next one. S will go to the next one. It is now referring to a node with degree 3. So it will try to store that value in D3, but D3 is already pointing to, it's non-null. It is pointing to some node. Therefore, D3 is pointing to a node with degree 3. S is pointing to a node with degree 3. Link them, okay, link both. So that is going to create a tree with degree 4, okay. Let us say this is made into degree 4. This is made into degree 4, 3 is made into degree 4. Now store the reference in D4. Now D4 will refer to this node. S will proceed further. When S proceeds further, S will refer to this node. Its degree is 1, D1 is empty, so D1 will refer to this node. It is a doubly linked circular list. You come back here, and when you come back, S will now point to this one. Its degree is 3, D3 is empty, therefore D3 will point to this. It will go to the next one, and when it goes to the next one, S will point to this node. Now you look at D1, there is already a tree with degree 1. Since there is a tree with degree 1 pointed by D1, D1 and S will be linked. When you merge D1 with let us say that one is merged with this, then D1 is gone, this is also gone, and this has become 2. This has become 2, and when you try to put in D2, D2 is pointing to something. Therefore, since D2 is pointing to something, D2 and S will be linked. So that will have the following effect. The D2 link will be knocked out. Let us say this has gone under the other one. In that case, this will go under this. Therefore, this will become degree 3. That has gone under this. Now S will be pointing to that. S will be pointing to the 3. So you will try to store S in D3, but D3 is already pointing to a node in the root list. That also has degree 4, degree 3. Therefore, this and that will be merged, which means I am going to, let us say I am putting that under this. In that case, this node will vanish, this S will vanish, this 3 will vanish. This will become 4, this will become 4, and S will point to this. And now you want to put this in D4, but D4 is non-empty, it is referring to some other node. Therefore, S and D4 will be linked. When you link S and D4, let us say that comes under this. When it is coming under this one, this is gone, all those things are, that is gone, and this has become 5. And you try to store the reference in D5. D5 is null, therefore D5 will store here, and D3 is already eliminated, and D3 is gone. it has become 5, therefore now value of S is stored. Now let S move. When S moves, S will move from here to this. S will move from here to this one. Now D0 will be pointing to this, and when it moves again, all right, it has come to the beginning. So for example, the name, wherever the name is, and the name H, whenever one node goes down, if name is referring to that, it can be shifted to the left, because name should always point to the root. So that way the name, so when S hits the name again, for example the name might be over here, and when S goes to the next, it will hit the name and you can stop. S made one full scanning. Okay. So now you see that this has got only, the root list has got only 2 nodes and their degrees are distinct. So this D array is a very interesting bookkeeping mechanism where Di maintains a pointer to a tree whose root has a degree I. If the scanner finds a tree whose root has degree I, then the tree pointed by scanner, the tree pointed by Di are linked, and a tree with degree I plus 1 is created. Now we may store the pointer to I plus 1 if that I plus 1, if you do not have a tree with degree I plus 1. But if you already have a tree with degree I plus 1, again you have to link it. You have to keep linking it until you get a tree whose degree is not there at all before. At that point, store whatever the node pointed out by S into the corresponding Di. So by doing this kind of a bookkeeping mechanism, we can consolidate it and finally arrive at a tree which consists of only distinct degrees. There won't be any 2 trees with same degree. If we have found 2 trees whose roots having the same degree, then we are linking them up. So this is called the consolidation process, and the consolidation process finally leaves a tree with distinct degrees. Okay. So what is the actual complexity and what would be the amortized complexity of this one and other things, we are going to see in our next session. In fact, that is where you are going to also find out why this structure is called the Fibonacci heap. So far you haven't seen anything connected with the Fibonacci numbers or Fibonacci sequences. So you might be wondering why this data structure. It's just a bunch of trees linked up at the root level in a circular list. Why should you call them as a Fibonacci heap? We will see the connection for connection between this data structure and the Fibonacci numbers by looking into certain structural properties and the amortized complexity analysis. That we will discuss in our next session. Thank you.